In 2018, a global e-commerce platform running a flash sale discovered that customers in different regions were seeing different prices. The discount had been written to the database, but the database was distributed across multiple nodes in multiple regions, and the write had not propagated everywhere before the sale went live. Some nodes had the sale price, some still had the original. Both prices were being returned by the same system to real customers, completing real purchases simultaneously. By the time the engineering team identified the cause, thousands of orders had been placed at inconsistent prices. The platform honored every one of them at the price the customer had seen. Every node was working correctly. The system was behaving exactly as designed. Eventual consistency is a design choice distributed systems make when they prioritize availability and speed over the guarantee that every read reflects the most recent write. In a strongly consistent system, a write is not complete until every copy of the data has been updated. Every subsequent read, regardless of which node it hits, returns the latest value. That guarantee is expensive. It requires coordination between nodes, which costs latency. If nodes cannot reach each other, the system must choose: return stale data or refuse to respond. Eventual consistency trades that guarantee away. Writes are accepted immediately on one node. Other nodes catch up later. The system promises that if no new updates arrive, all nodes will eventually agree. It makes no promise about when. That word, eventually, is where most of the problems live. Eventual consistency is not a softer form of strong consistency. It is a different model with different rules. Under eventual consistency, the window between a write and its full propagation is a period where different parts of the system hold different versions of the data. During that window, reads can return stale values. Reads from different nodes can return different values. None of this produces an error. A read returning the latest value and a read returning data from 30 seconds ago look identical to your application. The system cannot tell the difference, neither can the user. 3 failure patterns emerge from this reliably. The first is read your own writes failure. You write a value. You immediately read it back. You do not see your write. The read landed on a node that had not yet received the update. From the user's perspective, the change did not save. From the system's perspective, everything worked correctly. This is one of the most common and disorienting failure modes for applications built on eventually consistent stores, especially in user-facing interfaces where users expect to see what they just did. The second is stale reads under load. During periods of high write volume, replication falls behind. The gap between what the primary node has written and what replica nodes return grows wider. In normal conditions, replication lag is milliseconds. Under load, it can be seconds. During a spike, longer. The system continues to serve reads from replicas without indicating those reads are stale. Users and downstream systems make decisions based on data that is no longer current, with no signal that anything is wrong. The third is write conflict. In systems that accept writes on multiple nodes simultaneously, 2 nodes can accept conflicting writes to the same key at nearly the same moment. Both writes are valid. Both nodes believe they hold the authoritative value. When the nodes synchronize, the conflict must be resolved. Many systems use last write wins. The write with the later timestamp survives, and the other is discarded. Last write wins is simple. It is also silent. The discarded write is gone. No error is raised. No record of what was overwritten is kept. 3 approaches manage this. The first is session consistency for reads. Many distributed databases offer read your own writes consistency as a configurable option. Under this model, reads within a session are routed to the node that accepted the write. The read waits if that node's changes have not yet propagated. This does not make the system strongly consistent across all operations, but it closes the most user-visible gap, the one where your own changes appear not to have saved. The second is tunable consistency at the operation level. Systems like Cassandra, DynamoDB, and Cosmos DB let you specify a consistency level per read or write. A quorum read requires acknowledgement from a majority of nodes before returning a result. This means the value returned reflects at least one node that has the latest write. It costs latency. For operations where correctness matters, price lookups at checkout, inventory availability, account balances, that cost is worth paying. For operations where stale data is acceptable, browsing a product catalog, loading a recommendations feed, eventual reads are the right call. Tunable consistency lets you make that decision at the operation level rather than for the system as a whole. The third is replication lag monitoring. The gap between primary and replica nodes should be a first-class operational metric. Monitor it continuously, not only when a problem is reported. Alert when lag exceeds a threshold that matters for your workload. Replication lag tells you how stale your replica reads are right now. During normal operation, it confirms the system is healthy. During incidents, it tells you exactly how far behind each node is and which reads are most at risk. Without this metric, eventual consistency operates invisibly. With it, you can see the gap. The e-commerce platform from 2018 introduced quorum reads for all pricing and inventory queries during high-traffic events. Standard browsing remained eventually consistent. The cost was additional latency on checkout critical paths. The benefit was that price reads during flash sales returned the same value across all regions. Eventual consistency is a trade-off, not a failure. But it is a trade-off with real consequences when its properties are not understood. The system will accept your write. It will return reads that contradict it. It will resolve conflicts without telling you. It will do all of this without raising an error. The gap between write and convergence is not a defect, it is a deliberate property. What you build around that gap is the part that requires your attention.